Let's start with the second block of the session, scalar fields and cosmology, and it should be renamed boson fields and cosmology. But anyhow, thank you to everybody for attending to this BS1 second block session. And we begin with the talk of Jorge Cervantes, and the title of his talk is Nonlinear Perturbative Theory of Structure Formation for Modified Gravity. Thank you very much, Jorge. The floor is yours.
All right. Let me. Okay. Do you see the screen?
Yes.
Okay, thank you very much to the organizers. Alfredo, thank you for the invitation. And I will be talking about, as the title says, nonlinear perturbative theory of structure formation, but not for lambda CDM, but for extended models of gravity, for modified gravity. And well, the talk of the planned talk is first a motivation of modified gravity, why to consider alternatives. Then I will explain baryon acoustic oscillations and redshift space distortions. And then I will go to the perturbative part, that is the Euclidean perturbation theory. And then I will go to Lagrangian perturbation theory for modified gravity. And then I will go back to Euclidean perturbation theory for modified gravity, but considering redshift space distortions. And at the end, I end with a perspective of this. Well, what options do we have? Well, to consider a dark component has dark energy, for instance, and dark matter. That is usual. But what is important here is that what we observe is something that we call T-minus observed, and the rest has to be in some form of fluid or some form of dark components. Typically, the lambda CDM model assumes that the dark part is given by the cosmological constant and dark matter. The cosmological constant can be also, well, it's more thinkable as a dark geometry part, and we would have a dark part, dark geometry, that is the cosmological constant, plus something dark that is the dark matter. But in general, one can have here in T-dark, in G-dark, a collection of terms or functions of them that match the observations, because the observations are, by definition here, sum has another term. And we will consider, in general, modified gravity, but we can think of modified dark energy models also has modified gravity, at least a first order perturbation theory. Well, and why modifying gravity? More on that. Well, I borrowed these plots from this paper below, and it plots the curvature and the gravitational potential in different astrophysical events. For instance, here we have neutron stars and black holes, stars, galaxies, in the power spectrum of matter, and at the low end of the curvature. And the idea is to make measurements everywhere in this area to constrain the parameter ranges. At the right, we have the experiments that are being carried out to understand the physics. And for instance, in the cosmology part, is Planck at the bottom part, or the BAO experiments that, well, I will be talking about BAO here in the power spectrum also of matter. And in general, this area of low curvature is the area in which we are interested, and it is not very much well explored yet. So why modifying gravity? Because we have not tested enough at large scales, at scales of megaparsecs and beyond. Well, the accelerated expansion of the universe implies dark energy, or some kind of constant dark energy that is the cosmological constant, or some kind of dynamical dark energy that could be a scalar field, or some kind of modified gravity. We still don't know. Dark energy is mostly testable at cosmological scales and mainly at background level. We don't know, we know nothing of dark energy, only that it expands in an accelerated manner the universe. So in principle, the expansion is measured at background level. When we have modified gravity, we have an extra force, an extra gravitational force. And this force could act at different scales, not only at cosmological scales. And because we know that at local scales, planetary scales, let's say, we have essentially GR, or Newtonian dynamics plus corrections of GR. We know that there are not other force that is playing a role there. So we need a screening mechanism that shields this force, that turns off this force at local scales. For instance, this mechanism, there are three screening mechanisms to achieve this. And typically, when one has high density environments, for instance, near the sun or near a star, this force turn off, and we have a standard gravity. For instance, if we plot the force against the Newtonian force, this cartoon, and we start from the right to the left, from the very right, we have the horizon scales, very big scales, and then the field force appears at some megaparsecs scales, or tens of megaparsecs. But due to the screening mechanism, that is part of the complexity of the modified gravity model, turns off the force and brings the force to the extra force to zero, in order to have the force equal to the Newtonian one at local scales, or GR1. So our aim is not to prove or disprove a particular modified gravity model, but to test gravity at cosmological scales, where the screening are turned off. When are turned off the screenings, then the field force appears and makes here some effect on the gravitational potential, and that affects the structure formation of matter. Well, what are the large scale structure observables? Well, there are few. I will be considering the D-stock CMB and the matter power spectrum. That's all we know. This plot here from the Planck WMAP collaboration shows a cartoon of light at the last scattering surface, how it is emitted here, and it's measured at the right where the satellites are now. The last satellite was Planck, but it will come a new generation of satellites that will measure in more detail light, the light, sorry. And on the other hand, the matter power spectrum measures the statistics here of the matter distribution here in very large scales. Well, and these statistics is the power spectrum of light and of matter, and has all, we know these plots, especially the left one of the CMB. It is a very detailed plot of the temperature fluctuations against the angular scale, and it was measured so precise that it's not easy to have a theoretical model that can accomplish this feat. However, the lambda CDM model fits very well, which is the data, and this is the green part, the green line. On the other hand, the distribution of matter here and of galaxies can be plotted by, for instance, the Planck compilation 2018 had this plot, and here is the area of structure formation for galaxies in cluster of galaxies. And we are interested to study this part of the plot. I would say the physics involved in the CMB is the physics that's prevailed from the very beginning of the universe, nucleosynthesis, and until the last scattering surface, when the universe was 380,000 years old. And this physics is essentially linear physics. It's complicated because there are collisional terms that have to be treated in a particular manner, but in principle it's linear physics. And in the matter power spectrum, it has a linear part that is where precisely the linear perturbation theory is valid in this area until roughly k equals to 0.1, more or less here. I don't know if you see the cursor, my cursor that I'm using here, but well, I will be pointing here.
We do.
And do you see it? Sorry.
Yes.
Okay, thank you. And there is a nonlinear part, and this nonlinear part, gravitational part, is what I will be talking about this transition here. Well, BAO, baryon acoustic oscillations, and redshift space distortions are two important characteristics or features that has the power spectrum, and we have to explain this to really understand what is happening here. Well, imagine for the moment sorry, are you hearing me now? Yeah. Well, the BAO is its form as follows. Imagine an initial perturbation, and the content of the universe is dark matter, gas, that is protons and basically photons and neutrinos. And the perturbation in the metric, let's say, perturbs all the components, all the density components, pressure components, and everything there, all the variables. And the universe is expanding, and the neutrinos escape because they are not tied to matter in a fundamental way, because we are thinking in times that are much later than when the neutrinos were coupled. And the neutrinos go out, the gas, the barium photon gas, that is the red and blue part, they also escape from dark matter. They are not coupled only gravitationally. Dark matter only gravitates. I'm thinking in cold dark matter. And the things evolve in around the last scattering surface. the gas, the protons and the baryons separate, the photons escape, and the baryons stay gravitationally in a place, and now begins a gravitational attraction between the dark matter that is 5 times more than the gas. So the gravitational potential wells of dark matter attract the baryons that are there, the gas. And at the end, one has around a radius of 150 megaparsecs, a bump here in the density of baryons in dark matter. And this is the BAO. This scale, the 150 megaparsecs, is the standard ruler that now we use to measure gravity, for instance, and to measure indirectly the amount of matter, the amount of baryons that are there. Well, I have a video here that I want to show. It's an explanation of how in 3D this is formed. One have an initial perturbation, as I show you. It forms this bump at 150 megaparsecs. And but in the early universe, we have not only one perturbation, but a collection of distribution of perturbations in what it forms is a complex structure in which you will have in rings a little more, and in the center, a little more galaxies than normally. And this is an extra overdensity at these particular regions of galaxies. So what one does is to study statistically all this distribution of galaxies in the universe, and to study to construct a 2-point correlation function to study the properties of these galaxies. So one just construct the 2-point correlation function, and one see the BAO peak here at 150 megaparsecs. Okay, I go back to the presentation. This is BAO, and the baryon acoustic oscillations can be thought as a perturbation. Well, the information of the, well, I explained how it happens, but the initial perturbations here translates to this standard ruler, to some distance that has an overdensity every 150 megaparsecs. One find a little more galaxies than in other places. And the fluctuations here are very small. At the beginning, when the universe decouples, the fluctuations begins to grow, and the fluctuations are very small. But eventually, nowadays, these fluctuations can be of order unity, and we can measure that. For instance, if we are, this is a map of galaxies. Sorry, I didn't say that. This is of more or less 10 years ago of the BOS collaboration, perhaps. I don't remember exactly. But we are here in the center, and we are looking at different angles in measuring the different points that are galaxies, and see the structures that are formed, and we can measure also this feature, the BAO feature, in every direction. So what one can measure is this distance, well, the angular diameter distance, that is the distance of the BAO feature. S would be the 150 megaparsecs, and is given by the sign of the angle And in this distance depends on the cosmology that is between the BAO and us. So it depends on the cosmological parameters. But given a theory, for instance, lambda CDM or modified gravity, we can compute it and extract the information of the cosmological parameters through this method. We can one can also measure the line of sight distance, this distance here, that it would be also S, because it's a cycle here. It's a cycle and it's symmetric. So this distance is given simply by this expression here. This Z is the redshift of the galaxies there. In H is the Hubble parameter. Well, one can measure these distances, and through these distances, one can measure the omega parameter, but one can also measure the 2-point correlation function, as I was showing in the video before, and this bump is here in 150 megaparsecs. And the whole distribution has more information, has also information about the early universe. So it is quite interesting to study the whole form of the 2-point correlation function or the matter power spectrum. Well, the other aspect is the distortions in redshift space, because we don't see dark matter. What we see is our photons. Photons are stemming from galaxies, from normal galaxies. So normally they are not the same thing. They are close related, but dark matter, well, galaxies are seated where the gravitational potentials of dark matter are. But imagine that we have a ring of galaxies here, and we are at the bottom. So if we see a galaxy that is here, so at the top, we will see that its redshift will be in this direction. So it will be a blue shift to us. In the redshift of this galaxy would be a redshift redshifted to us if we are here. So this is gaining, the photons are gaining energy here, and the photons are losing energy here. And the universe is expanding everywhere. So if we are at the bottom, we see that in redshift space, we change coordinates from normal coordinates to redshift. That depends on the local velocity here of these galaxies, the peculiar velocities. One sees the distribution of matter has a squashing. This squashing effect is observed and is due to the different velocities here that we are having here in a local gravitational collapse in the universe. And this velocity here depends, of course, on the gravitational potential that we have there. If we have a field force there, so the velocity will increase or decrease depending on the sign of the force. And that is what we want to measure. I mean, we want to measure the effects in the redshift space distortions due to gravity. Well, when one considers the power spectrum, on the one hand, one has the distribution of dark matter given by P delta delta, and the distribution of galaxies due to this distortion has to be changed by this F. F is the growth rate, where D is simply the growth factor here that an initial perturbation that depends only on the initial condition grows in the matter part. In galaxies are biased by a term that is also here. So in the galaxy power spectrum, we have two extra terms, the bias and the F term here. And the mu is the angle of the particular mode K again in the line of sight in which we are looking at the object. Well, in lambda CDM, this F is more or less omega m, but in omega m to the 0.6. But in modified gravity, we will see that this F depends also not only on time, but depends on the scale, on a particular scale. Well, and the observations already 20 years old of the squashing effect were done by John Peacock et al. And one can see this effect very nice here. And in the power spectrum, one can consider this power spectrum and integrated in different contributions of monopole, quadrupole, hexadecapole, etc. By integrating this expression over the angle mu with the Legendre polynomials, and one can compute the different contributions here. And this can be compared with directly with measurements, a work presently work by Ivanov, that normally to compare large scale structure data, the power spectrum with the theory is very complex. It's a very complex subject in which one have to do simulations, mocks, and a very elaborated technique. But for instance, this is, well, the first approach, also with Amico, they put forward the idea to compare directly the data with the theoretical models of the type that I will present here. Well, the evolution of small overdensities is as follows. In the early universe, at last scattering, essentially the universe is linear. After last scattering, light keeps the couple and therefore linear, but matter gravitates to form more complex structure, and a hierarchical clustering forms in which the small scales collapse first, then the larger scales, and the nonlinear collapse show up first in the smaller scales. So in fact, a star is a very strong collapse, and it's very nonlinear. But for instance, at distances of the horizon, the collapse is linear still. So large scale forms can be measured through galaxy surveys such as EVOS or DESI. And one can measure distances, as I say, the angular diameter distance, that is background dynamics, in the full point statistics associated to the galaxy distribution that has a linear part and a nonlinear part too. So to study perturbations, there are nonlinear perturbations. There are two approaches, Eulerian and Lagrangian, and I will go to it now. Eulerian perturbation theory is based on the Boltzmann equation with the right-hand side equal to 0, because we are considering here dark matter particles. And one built the first moment with the Boltzmann hierarchy formalism to define velocities, to define these tensors here, and a possible stress tensor also, in which, well, the delta is the overdensity, is the density that depends on the space and time over the background density, that is a mean density in the universe. And this will account for our growth of matter over densities. And the continuity in Euler equations are given by, as known, by these two terms, in which one has here, for instance, the Hubble parameter. I think tau is the conformal time here. U is the velocity of particles. And one has here, for instance, the gravitational theory. So here it enters the gravitational part through the Poisson equation, of course, the cosmological Poisson equation that has the Hubble parameter here. But if we have a modified gravity term, we will have to sum some other terms here. It will be clear in the next slides. In Fourier space, one can also consider this. It is more common to treat Fourier space to construct the power spectrum, which is in the Fourier space, and the same equations are written here. But now we have these integrals here, these convolutions that appear in. If you see, sorry, let me go back here. We have some linear terms, some non-linear terms here. For instance, this term here, this term here. These non-linear terms here are now at the right part, but are encoded in these two parameters, alpha and beta, that are on the right-hand side here and here. So we have an integral differential equation here that are coupled and that we have to solve. Solutions has a sum of different terms that depends on the scale factor at different orders, and the solutions are given by this hypothesis, in which we have these integrals here that depending on the order. We have the linear part. The linear equations can be solved. All the right-hand sides are 0 here and can be solved normally depending on the gravity model, but they can be solved analytically or numerically. And that this gives us the linear part, the delta 1 or the theta 1s. And these deltas here is this linear part, but the solution, the structure of the solution is given by these functions f and g that are called the kernels. And the kernels are found by substituting this solution into the equations. And normally the kernels are known for the lambda CDM model. The first kernels are trivial. The second order perturbative solutions are given by this, and the third order are also known, are more complex that I don't write here. So with these solutions, one can construct then the deltas. One does statistics, one does construct the correlation function, or the Fourier counterpart, that is the power spectrum. And also for the bi-spectrum and tree-spectrum for higher order statistics if one wants. So the perturbative expansion sums the different orders, linear order, second order, third order, etc. In all these terms, in the two-point correlation function or power spectrum can be grouped in what is called the three-level one-loop terms and two-loop and higher loops, in which every loop has the same type of order of magnitude of contribution. We see here is 4 order, here is 6 order, and it is useful to consider in blocks the different contributions. Well, we borrow the language from quantum field theory. We understand these loops has interactions of two density of the two overdensities in the linear part at different places, at different scales. K is the wave number associated to some wave, some distance between galaxies, and the interaction of this overdensities is given by the kernels. Then this produces an overdensity of second order. And also for any order, one have this type of interactions. And for instance, for the one loop, one have this type of terms. One have combinations of delta one with this delta one, and one have these terms delta one with delta three stemming from this type of interactions. And at the end, the one loop can be thought as a linear part plus a next to leading order here, where the next to leading order are given by these two terms, and these two terms are given by these integrals. And these integrals are complicated because are in 3 dimensions here of the momentum, and the kernels are here, the power spectrum is here, and well, this is how it is. This is the standard one loop in lambda CDM, and I borrowed these diagrammatica and equations from Dodelson and Schmidt book. Now let's go to the nonlinear part for modified gravity. So in this case, we have the previous equation that I showed, the continuity and the Euler equation, but we have also the new Poisson equation. Now psi is the gravitational potential, but now we have an extra term here. And this extra term is given by the scalar field that modifies gravity. And remember that any modified gravity, almost any modified gravity that people consider now can be written as a scalar field dynamics with some potential and kinetic term. So this is what is called the Jordan frame. The scalar field is given by the Poisson equation, in which we have a linear term, well, a standard term, plus some nonlinear terms that I just write like that. For instance, in Fourier space, if one writes this in Fourier space, the nablas square, the nablas goes to k squares, and the nonlinear part is given by this term. This term has also a linear part. You look at the information that comes from the modified gravity models will be in these capital M's here, M1, M2, M3, until one loop. This was developed by Kazuya Koyama some years ago. And for instance, considering one particular model of gravity, the Husavitsky model with n equal 1, has some precise n functions, and these functions define the gravity model. And we will be talking, when I show plots, that this parameter here, the f, the partial derivative of the f of r gravity with respect to r evaluated today is given by 10 to the something. I will be considering that is equal to, that n is equal to 4, 5, and 6. I will be considering 3 models here. But well, this is the gap. One has a modified Poisson equation. In this term is given by the Klein-Gordon equation. One have nonlinearities here. These nonlinearities are computed in the Fourier space through these integrals. Well, let me go back to Now to Lagrangian perturbation theory for modified gravity. This is the Eulerian part. Lagrangian perturbation theory for modified gravity, because I go back because this was the first paper that Alejandro Avilés, who is giving a talk later today, and I did some years ago, and it was the beginning for us to study nonlinear perturbation theory. And we began with the Lagrangian perturbation theory. In Lagrangian perturbation theory, one simply has here a displacement of the normal coordinates, and the displacement here will be the important variable. This variable, the displacement, is expanded in different perturbative orders. In the different orders can be given by this type of integrals, in which one has again another kernel, a different kernel, but it's also a kernel that encodes the solution here. And for instance, the delta can be given by a different orders, can be given by the different Laplacians of this displacement. So it's simply in another coordinates. Well, the type of equation one obtains here are complex. This is a function of time here, and one have different nonlinearities. Let me just mention two. One that is called frame lagging, that we have discussed it in the paper, in which one have the Laplacian of with respect to the Eulerian coordinates in the difference with the Laplacian in Lagrangian coordinates. This term is important to consider. And the other term that I want to mention is the nonlinearities that appears due to the different m's here, M2, M2 and 3, that depends on the gravity model. Well, one can construct the power spectrum. This is the definition, and one can write this as this integral. And to make the statistics, one computes here the ensemble average of this quantity. And psi, remember, is the main variable here. And in perturbation theory, there are different developments. At that time, one of the main developments, and today still, is the convolution Lagrangian perturbation theory that has a linear term, that is the Seldovich theory, plus two other terms here that are given by these expressions here, where these x and y's here loop to one loop are given by some integrals. One can also construct the correlation function for this theory, for the Lagrangian perturbation, for convolution Lagrangian perturbation theory, is given by all these integrals, and here are more integral terms, and the different terms are given there. But all this depends from the displacement. And then one can plot, for instance, for the model F4, when n is equal to 4, for the Husavitsky model, in which one has the power spectrum, for instance, some redshift in the past, set equal to 0.5, or today, set the redshift equal to 0, and we show here the part of the screenings here, not considering the screenings when one has no screenings here. And the screenings play an important role. When one sees here, it looks like a small correction, but the screenings are really important. It depends also on the units. So, and the points are simulations points from Bao-Lee that give us these points, and we plotted in the agreed band. It's very nice to around K.1, 0.12, maybe around here. Then begins the simulations begin to depart. In this area, the simulations are the truth. We think if we have the same cosmological model, we have to reproduce what the simulations are saying. Well, we studied in more detail the screenings of the growth functions. The growth functions are basically the growth of the overdensities. And we studied when the screenings turned on for different. Let's concentrate in these three plots here. There are configurations of exquisite, equilateral, or orthogonal distributions. When one has perturbation theory, one wants to compute a growth rate, a growth factor, how matter is growing. One has to consider a particular configuration of three particles, for instance, making a triangle that is squeezed, equilateral, or orthogonal. And we see that the squeezed part is the one that contributes most to the effect of gravity. And we see here when these terms begins to grow, and we discover that one can define a screening wave number here that is given by the capital M that depends on the scale factor times the scale factor here. Well, more details are in this paper that we did a couple of years ago with David Mota. One can also compute the 2-point correlation function. Remember that in 150 megaparsecs, that in these units is around here, where this bump is. The linear part that is very exaggerated, but when one considers non-linear terms, one have different curves here, depending on the gravity model that we are considering here. Well, and the last part is to study redshift space distortions, not only the bow scales in the wiggles that are here. These wiggles here are the bow wiggles, and we can study also what I was telling before, the redshift space distortions, and we choose now the Eulerian perturbation theory, and that is a recent work with some collaborators. So we consider different gravity models given by some function AK that depends on k on time, and some extra nonlinear term here. A and S will determine the specific models of that could be modified gravity, K-dependent dark energy. One can incorporate massive neutrinos in lambda CDM, considering some terms here, as Alejandro did in the recent past. One identifies the effective Newtonian potential. Remember that this is the modified Poisson equation, in which one have the standard term for pi g, rho of the background, and mu, that is a deviation of the constant g, let's say. One can understand like that. The nonlinear orders can be expanded, has integrals, as before. These terms are these integrals here. And then we have the Fourier equations, the Boltzmann equations in the Fourier form, that are the continuity equation in the Euler equation, in which one have, again, the alphas and betas that we had, and we have these extra terms that we'll speak for the modified gravity models. For instance, to linear order, these terms are zero, and one can find this. Thank you. One has this equation, one can solve it, and the growth functions are given, give the solution of this. This is the initial condition. Well, the higher order solutions can be found again with subkernels, and the kernels are found from the Lagrangian kernels that we had, one can also deduce the Eulerian kernels. This is explained in another work that is there. Here is the kernels for the second order perturbation theory. We have computed also for the third order. And these A's and B's are these functions here, and they follow some differential equation that we have to solve in a complex manner. With these solutions, one can then construct the power spectra, the different terms to one loop, for instance, for any modified gravity models. And also, we have to consider the bias between galaxies. All that I said before is for matter, but now we have to consider delta and theta for galaxies, and these galaxies has some bias terms, but there are, when you consider to one loop, one has, and for modified gravity, one has different terms here, and then the bias can be written formally as some operators, but let me go a little faster here. And the power spectrum for tracers then finally are given by all these terms. But until now, this is the power spectrum for galaxies, but we haven't considered redshift space distortions. Now we consider redshift space distortions in which the velocities here are given by the growth rate, and theta is the divergence of the velocity. Essentially, well, it is the definition practically. And again, one construct the deltas for galaxies in redshift space coordinate and the power spectrum. And the power spectrum is given. See, these terms depends on the velocity, on this velocity that, recall, this velocity depends on the gravitational potential, of course. And this depends on this guy here, that is the moment expansion that is given by these statistics. And one can compute this. In the paper I was showing before, we consider an ansatz here for this expansion, in which we separate the different moment, all the different terms or orders with some particular function here remember, mu is the cosinus of the line of sight and a particular wave mode. Well, to linear order, one obtain a generalized Kaiser term. This is the linear term plus this term here that now depends on K. Before, for the Kaiser theory, which is the linear theory of RSD, solely depends on time. And we call nonlinear Kaiser all these terms that are to the second order in this expansion here. And well, one can construct all the terms to one loop, and all the terms are given by this guy plus two extra terms that I just put there. Are sum of different integrals here that one has to do. And lastly, one needs to consider effective field theory contra terms, because in a standard perturbation theory approach, the loop integrals are computed over all internal momentum space. However, it does not hold for all scales, so we have to cut the integrals and let me say economically, and one has to introduce these counter terms in the normal power spectrum. And these counter terms has a free parameter here that comes from the impossibility to integrate high energy modes, the ultraviolet modes. So considering these counter terms, one has then the final power spectrum for galaxies or for in redshift space in the momentum expansion approach, plus some counter terms in short term. And then one can compute the power spectra and compare with simulations. And this is what we did. We compare again the monopole, quadrupole, and now the hexadecapole that is more noisy. And considering the counter terms, the agreement with the theory is not only to k equal to 0.12, but until 0.25 or something. And this is a recent work that we published. And the perspective finally is to apply all these framework to real data, not only to simulations, perhaps in a direct way through an MC code that efficiently computes the cosmological parameters directly from the cosmological data of the power spectrum, as Ivanov did that I mentioned. And with that, I stop here.
Okay, thank you very much for your interesting talk. Are there any questions? If you have a question, raise the hand. No? Okay. If there is no question, then thank you very much, Jorge.
Okay, thank you. All right.
Okay. The next speaker is Jorge Delgado, and he will talk about time-like circular orbits and efficiency of compact objects.
Yeah. Thank you.
Jorge, the floor is yours.
Okay, thank you. Hi, I'm Jorge Delgado, and I'm here to present a recent work that will appear tomorrow on Archive about time-like circular orbits and efficiency of compact objects. It was shown in this work that very generic horizontless objects, when they have light rings, that light rings appear as a pair, one of which is unstable, the other is stable. The same authors also some years later show that for the case of a black hole, a very generic black hole, they always have at least one light ring which is unstable. These are quite interesting results, but they only study the null geodesics. But here I'm more interested in study the time-like geodesics and seeing if this type of structure of light rings implies some structure for the time-like case. And in fact, as I will show you, it does. So this is what I'm going to do in my first part of the presentation, and I will show how to obtain these results. So you can start by considering a very generic spacetime. It's stationary, asymmetric, asymptotically flat, and in four dimensions. Then with the symmetries and with some gauge choice, you can write this very generic metric, which basically represents a rotating object. And then we also assume a north-south Z2 symmetry, which implies that the equatorial plane is a total geodesic submanifold. Then we just have to study the cyclic orbits on that equatorial plane. For that, you can start by writing a Lagrangian of a test particle, in which this she is either -1, 0, or 1 if you are considering time-like, null, or space-like particles. Then you can introduce the energy and the angular momentum of the particle and can rewrite the Lagrangian in this way, where a and b are these two functions. The b here is always positive. Then you can define effective potential in this way. And we do this because in order to have a circular orbit, then the potential and its first derivative must both be equal to 0. This gives these two quite simple results. And by solving this, you can find the cyclic orbit. Then with that result, you can study the stability by looking at the second derivative of the potential and seeing if it is positive or negative. If it is positive, then you have unstable orbits. If it is negative, then you have stable orbits. For a very generic space-time, when you solve these two equations, you get a pair of solutions, one of which corresponds to co-rotating orbits, which we use the plus sign, and the other is for counter-rotating orbits, in which we use the minus sign. Now let's start with null particles. So for null particles, circular orbits are light ring, as you already know. So you can take the two equations, you can write in this way, and you solve them. The first one will give you the inverse impart parameter, sigma, and the second one will give you the radial coordinate of the light ring. With that result, you can again look at the stability, and you get this expression. And here you can see that this quantity is always positive. The denominator is always positive because this is basically the B function that I talked about before. So you only have to look into the denominator. If it is positive, then it's an unstable light ring. If it is negative, again, it's a stable one. For time-like circular orbits, it's a bit more tricky, but you can simplify the results by introducing the angle velocity of a time particle measured at infinity. And then with the first equation, the potential equal to zero, you can define the energy in the angle momentum, in which they will be a function of the angle velocity. And here we have this beta function that I highlighted in red, which is equal to this expression. And I highlighted because it will be important later on the presentation. Then with the second equation, when the derivative of the potential is zero, you get an expression for the angle velocity, in which here this C function is a function that is given by this quantity. And again, I highlighted with a different color because it will be important in the next two slides. So for the when you get the time-like cycle orbits, you can look into its stability and do the same. So in most cases, what you have is a region where the second derivative is negative. So you have stable time-like cycle orbits, and then you have a region where the potential is, or the second derivative of potential is positive. So we have unstable time-like circular orbits. And in the threshold of these two regions, you have the region where this quantity is equal to zero, and usually this is called the innermost stable circular orbit, or ICO for short. But and this is what happens, for example, for Kerr and for Schwarzschild. But for a very generic ultra-compact object, that may be very solutions for this equation. And when that happens, we have to define what we call the standard ICO, which is the solution with the largest radial coordinates, such that the second derivative of the potential is equal to zero, and the third derivative is negative. This is just to ensure that above the ICO, we have always a region of stable time-like circular orbits. Then, if you remember for the C function that I mentioned before when we talk about the angle velocity, if it is negative, then there is no circular geodesics, either time-like, null, or space-like. So you could have something like this. You can have a region without any circular orbits where C is negative. Then you can have above it a region of stable circular orbits in which the C function is positive and the second derivative of the potential is negative. So between these two regions, you can also define some type of ISCO, in which here we define the absolute ISCO. So it is either the solution with the smallest radial coordinate such that the C function is equal to zero, and radially above it, slightly above it, the second derivative of the potential is negative. So again, this part here is just to ensure that above the ISCO we have stable time-like circular orbits. But it can also be the solution with the smallest radial coordinate such that the second derivative is equal to zero and the third one is below zero. So it's basically like the standard ISCO, but instead of being the one that is very far away from the object, is the closest one to the object. So now that I introduced all the quantities, we can now look into time-like circular orbits and what is the relation with light rings. the main result that I want you to take home is that the stability of a light ring determines the possibility and the stability of time-like circular orbits around it. And this can be shown by first realizing that that beta function that I highlighted before, which appear for the energy and angular momentum of the time-like particle, when that beta function is equal to 0, this corresponds to a light ring. And this can be shown first by considering some circular orbit in which beta is equal to 0. So we have something like this. You can solve this equation and you will see that the angular velocity of the time-like particle is equal to the inverse parameter, the inverse impact parameter. Then in order to show that in this circular orbit, in fact, we have a light ring, we have to show that the first derivative of the potential for null geodesics at that circular orbit is equal to 0. So if you write the first derivative, you get this, and then using this result here, and using the definition of the angular velocity for time-like particles in circular orbits, which was obtained solving this equation, this below equation, then we can show that, in fact, the first derivative of the potential for null orbits are in fact, or is in fact equal to 0. Therefore, we are on a light ring. Thus, when beta equals to 0, we are on a light ring. But why is this important? This is important because when we look to the energy of the time-like particle, the energy and the angular momentum, it goes like 1 over the square root of beta. So from this, we know that at light ring, both values diverge. But most interestingly is that since there is a square root here on the beta, then if you look on the region close to the light ring, if beta is negative, then the angular momentum and the energy are complex. Therefore, we cannot have any time-like circular orbits. In fact, what we have is space-like. So there will be space-like circular orbits. But if it's positive, then the energy and the angular momentum are real. So we can have time-like circular orbits. So we need to see if either case happen. For that, we do a Taylor expansion of the B function here, which at first order is just this part. You can compute this and we obtain this very long expression. But the main point here is that this quantity is always positive. This here is a square root, so what comes out of a square root is a positive number. Therefore, the sign of beta depends on the stability of the light ring and if you are above or below that light ring. So in order to be easier seen, here we have the case of an unstable light ring in which the region within is always a region without any time-like circular orbits, since the beta function is negative. And above it, we can have time-like circular orbits. For the stable case is basically the opposite. Outside or for larger radii, there's region without any time-like circular orbits, and within is where you can have time-like circular orbits. But we can go further because here we know that they are allowed, but we don't know yet their stability. So we can look into the stability. If we compute the stability, we have this long expression, but the most interesting part here is that on the light ring, beta goes to 0. So this term diverges. And since this term here never diverges, this is the one that the first term is the one that it's important close to the light ring. And since we are going towards beta equal to 0 through positive values, which are these regions here, where we can have time-like circular orbits, then this is a positive number. This is also a positive number because this is again the B function. So the sign of this quantity will only depend on the numerator or the sign of the numerator. So if you compute the numerator at the light ring, what we see is that this quantity is always positive. Thus, the sign of the denominator depends only on the stability of the light ring. Thus, completing our initial scheme, what we have is that we have an unstable light ring, and above it we'll have always unstable time-like circular orbits. For the stable case, will be basically the opposite in the sense that within the stable light ring, we'll always have stable time-like circular orbits. And this is the main result for my first part of the presentation. Then with this result, you can show that for a ultra-compact horizontless object, very generic, the region between the light rings, the existing two light rings, will always be a region of without any time-like circular orbits, because here beta is always negative. And in order to have within this region a new region of stable or unstable time-like circular orbits, beta, the beta function must be positive. And by continuity, beta must cross a point in which is zero. And as we saw before, when beta is equal to zero, we have a new light ring. So since here we are only considering these two light rings, we cannot add a new one. So this region here always must be always with beta negative, and therefore no time-like circular orbits. In a very similar manner, you can say that the region between the horizon and the unstable light ring, for the case of a black hole, will always be a region without any time-like circular orbits. And you can say the exact same argument. So here I show you how to obtain these two quite interesting results. But now I will go to the second part of my talk, and I will talk about the structure of circular orbits for several cases, several stars and black holes. So we'll see this structure appearing. And I will also talk about the efficiency. So the efficiency is the gravitational energy, which is converted into radiation as a time-like particle falls from infinity until it reaches the ice core, and is very easily computed through this equation. But as you may remember from the beginning of my presentation, we define two different ice cores. We define the absolute ice core and the standard ice core. So here, naturally, we always have the standard efficiency and the absolute efficiency. So the standard efficiency will be something like the falling particle, time-like particle that reaches the standard ice core, and you compute the standard efficiency. And for the absolute case, we have the particle which is falling and then reaches the absolute ice core, and we compute the absolute efficiency. So I will start by talking about stars. So I will talk about two different families of spinning scalar boson stars and one family of spinning vector boson stars. So here you can see the ansatz was used for the scalar field and the vector field. So let's start with mini boson stars in which the azimuthal harmonic index is equal to 1. So this M here. Here we have the action. And let's start by looking into the co-rotating orbits. So here, very simply, what I show you here is the maximal value of the scalar field as a function of the radial coordinate. We do this because this way each horizontal line corresponds exactly to one star solution. And you can draw or do this type of plots. For example, if you're far away from the star, you are on a region of stable circular orbits, the green region. But as you go closer to the center, you reach the absolute ice core, which is this point here. And then within that region, we have a region without any any circular orbits. You can also see, if you consider now a solution, a more compact solution, that it can start to develop a disconnected region of unstable time-like circular orbits. So as you can see here, and due to that that region, it will appear the standard ice core as well, as you can see. So if you compute now the efficiency, we see that here we have the efficiency. We see that the absolute efficiency starts from 0 and goes very close to unity. And for the standard efficiency, it only appears for solutions that are more compact. And we see that since the standard ice core appears a bit further away from the star, the efficiency will also be much more lower, so lower values. So here it's about 25%. Then if you go further up, the efficiency rises a bit. Now for counter-rotating orbits, here we have a more colorful structure. Since for some solutions there are this pair of light rings, in which the outer one is unstable and the inner one is stable. So here we see exactly the same picture that I showed before, in which we have the unstable light ring, which is the one outside, more outside, and for for bigger radial coordinates, we see that we have an unstable region. Then within the two light rings, we have the region without any time-like circular orbits, and then within the stable light ring, we have a region of stable time-like circular orbits. So if you compute now the efficiency for this case, the absolute efficiency is exactly the same as for the co-rotating case, but now the standard efficiency is quite lower, is very low values of efficiency. First, we see that it appears much sooner because the solution starts to develop this disconnected region of unstable circular orbits. And then with that, the standard ISCO also appears very far away from the star. Thus, the efficiency will have small values. And even if we go to more compact solutions, the standard efficiency stays more or less on the same values. Now we can move on to a different family. So we will consider now axionic boson stars, in which here is the action with this potential, which is based on the QCD axion potential, in which there's this FA, which we call the decay constant. And if this decay constant is big enough, then we'll approach the mini boson star case. But if it is close to zero, then we start to see different results. So for the co-rotating orbits, here we have the structure. It's not very, very different from the mini boson star case, but the unstable region appears sooner and appears furthest away from the center of the star. Thus, you already can see that the standard efficiency will have lower values for the efficiency. Then the absolute efficiency again goes from 0 to very close to 1, but doesn't go as linearly as it did for the mini boson star case. For the counter-rotating orbits, we have here again the structure, and it's similar, but the lines are a bit more curvy there, basically. But you already can see that, well, the absolute efficiency is again the same for the co-rotating case, and the standard efficiency happens much sooner. And since the standard ISCO appear far away from the center of the star, the efficiency also is very low. Now, moving on for the vector stars, we will study the Proca stars or the mini Proca stars. And for this case, the results are quite different. As you can see, for co-rotating orbits, all the solutions that we study in all space-time have a stable time-like circular orbit. So a particle could start in infinity and fall down all the way to the center of the star, never always on stable time-like circular orbits. So here, if we study the efficiency at the center, where we define the absolute ISCO, then we see that the efficiency goes from 0 very close to 1. For the counter-rotating case, we see that for a large part of the perimeter space is the same as for the co-rotating case, but more compact solutions can start to develop a region of unstable orbits. And if we go further, we can have solutions with two disconnected regions of unstable circular orbits, something like this. You have 2 yellow regions and 3 green regions. And if we go even further, they can also start to develop light rings. Now, so for the efficiency, the absolute efficiency again is the same as for the co-rotating case, doesn't change much. But the standard efficiency now is a bit different. So for these solutions here, the standard ISCO is here, so it's closer to the star, so the efficiency is a bit bigger. But as soon as the solutions start to have these two disconnected regions, then the efficiency drops a lot into smaller values. Now, let's focus on black holes. Here I will study two families of black holes. The first one is Kerr black holes with the synchronized axionic hair. So this is the black hole generalization of axionic boson stars. So the action is the same as for the axionic stars. And here we have the domain of existence where you can find this type of black holes. Then we have the Einstein scalar Gauss-Bonnet black holes, in which we have a real scalar field, which is coupled to the Gauss-Bonnet invariant. And here we have, again, as well, the domain of existence. Now, for the first case, we study this family with the same decay constant as for the axionic stars. And here we have a different plot, so I will explain you a bit better. So in this vertical axis, we have the efficiency, and here we have the dimensional spin. In this dotted blue line, we have the Kerr line. So we see that the efficiency of Kerr black holes goes from 6% for the Schwarzschild case until 42% for the excimal case. Then we have a region of this light blue region, which corresponds to hairy solutions that has a very Kerr-like aspect, in the sense that there is only one horizon event, only one light ring, and only one ISCO. So it's very Kerr-like. And even for those cases, you can have efficiencies that go very close to unity, and they are way bigger than comparing with the extremal Kerr case. Then you can look into the dark blue region. In this case, these black holes are what we call it non-Kerr-like black holes, in which there are some disconnected regions of unstable light rings, or even disconnected regions of no time-like circular orbits at all. This happens because for some solutions, the scalar field can develop a pair of light rings. Then even for this case, there are some solutions that have bigger efficiencies than the ones for Kerr. So even for those cases, we can have quite large efficiencies. Then moving for the counter-rotating orbits, the plot is similar. So here in blue, we have the Kerr line. And for both cases of Kerr-like and non-Kerr-like black holes, we see that it's also always possible to have efficiencies much larger than the Kerr case. Now, moving to the last family of black holes, it's much easier because all solutions here are Kerr-like. So when we look into the efficiency, we see that for slow spinning black holes, these area black holes always have bigger efficiencies when comparing to Kerr. Only for fast spinning black holes, after this point here, we see the reverse. So from here on out, the Kerr black holes have more efficiency than the black holes in this theory. For the counter-rotating case, we see that these black holes always have more efficiency than when comparing to the Kerr solutions. But this difference starts to decrease as we increase the dimensional spin. So to sum up everything, and for you to take these ideas home, we show you that for a very generic stationary asymmetric and asymptotically flat compact object in 4 dimensions with a Z2 symmetries, the existence of light rings dictates the possibility and the stability of time-like circular orbits around it. And with this result, I show you that ultra-compact horizon objects, for ultra-compact horizonless objects, the region between the two light rings is always a region without any time-like circular orbits. And for the black holes, the region between the horizon and the unstable light ring is again a region with any time-like circular orbits. Then for the efficiency, we study two families of spinning scalar boson stars, but we saw that for the absolute efficiency, both co-rotating, counter-rotating case are the same, and the efficiency can grow very close to the unity. Then for the standard efficiency, we saw that co-rotating orbits always show larger efficiencies than the counter-rotating case. And we also saw briefly that the presence of soft interactions tends to suppress very, very slightly the efficiency. Then for the vector boson stars, we saw that in terms of the absolute efficiency, both for co-rotating, counter-rotating case, it's possible to have stable circular orbits until the center of the star. So we computed the absolute efficiency at the center of the star, and we saw that it can increase almost until 100%. For the standard efficiency, we saw that counter-rotating orbits for the more compact stars have disconnect regions of unstable time-like circular orbits, and for that reason, the efficiency drops to very small values. For the black holes, we saw that there are some. For the first family, we saw that there are some Kerr-like and non-Kerr-like black holes, in which these non-Kerr-like black holes have disconnected regions of unstable and no time-like circular orbits. For the co-rotating orbits, we saw that the efficiency can be much larger than the efficiency for Kerr black holes and can grow very close to unity. For the counter-rotating case, we saw that the efficiency is much smaller than the one obtained for co-rotating orbits. But anyway, it's always, not always, but almost all, for most solutions, is larger than the efficiency for Kerr. Finally, for the last set of solutions, black holes, we saw that the structure of cycloreds is very identical for the Kerr case. So all the solutions are Kerr-like. We saw that for co-rotating orbits, the efficiency is larger than the Kerr one if the dimensional spin is small, but if it is large enough, the opposite happens. Finally, for the counter-rotating case, the efficiency is larger than the Kerr, is always larger than the Kerr, but those difference starts to decrease as the dimensional spin decreases. So thank you for your attention.
Thank you, Jorge, for your very nice and interesting talk.
Thank you.
We have time for a couple of questions. If you have a question, please raise the hand. Jorge, Cervantes.
Yeah. Well, I don't work in this area, but I wonder if you have considered these bosons has a condensate. Of course, one has to introduce temperature and things that maybe, I don't know, extra degrees of freedom there. But it will be interesting to know if they form a condensate, a boson condensator.
Well, one of the interpretation for this type of boson stars is exactly that: is a boson condensate, boson Einstein condensate that is self-gravitating. So it's already something like very similar.
Okay, so in principle, it is a condensate in that case.
Mm-hmm.
All right.
I believe so. Yes.
Thank you.
Yeah, welcome.
Are there any other questions, comments, or remarks? If not, we thank Jorge Delgado once again.
Thank you.
Now the next speaker is Alejandro Avilés, and the title of his talk is Testing Modified Gravity Theories with Marked Statistics. Please,
okay.
Alejandro.
Thank you very much. Can you see my screen and my cursor?
Yes.
Okay, so I will talk about a novel method to constrain modified gravities using different statistics than the usual ones in cosmology. The usual ones are the power spectrum and the correlation function and their generalizations to higher orders, so 3-point correlation function by spectrums, and so on. So this is more than testing modified gravity. It is like toward testing modified gravity, because this technique has only be tested against simulations. We have to test it. We have to test it against real data. So I think soon this will be done. And I will talk about mainly about these 3 papers. So the first 2 are analytically, and the third one is more observationally and from the simulation sites. So the third one is part of a group which is part of the DESI collaboration. So it is intended to give these ideas to the DESI, to test with DESI in the near future. Okay, so the idea is not coming from this paper. The idea is coming from a paper by Martin White in 2016. But Martin White didn't develop too much the idea, so a lot of papers came after that. So I have worked with several collaborators in these papers, and they are people from observation, from simulations, and from theory. Okay, so I will start. Okay, this is the outline of my talk. So I will give a motivation, why use other statistics besides the standard ones. Then I will define what is a marked density field and what is it for. And then I will talk about the marked correlation function and the marked power spectrum, which is basically the Fourier transform of the correlation function. Okay. So to start with the motivation is this plot. This plot comes from the Gauss paper. Gauss stands for Gravity and the Universe from Large-Scale Structure Formation. It is a planned galaxy survey. I don't know if it will be accepted. But the nice thing about this plot is that the growing is exponential. The y-axis is giving you the number of objects observed by each one of these galaxy surveys. So it is a logarithmic scales in the y-axis. So this is growing exponentially. Right now we are about here. We are starting with DESI. And we finished BOSS, which is a continuation of the Sloan Digital Sky Survey. And after BOSS, they came eBOSS, which is the extended BOSS. Here are other surveys that are not counted for, because this is only, here you can see only spectroscopic surveys. And there are also photometric surveys as the LSST, which now it changed the name to Vera Rubin Observatory. And LSST will be about here, but the science already started. And it will be start to measure in about 4 years, and it will measure for 5 years. So we expect to have the final results of the LSST in about 9 years. So as I said, we are about here. DESI already started to measure, but we have to wait about 1 year to have the first results, the 1 year results. And it will measure in principle for 5 years. So the next thing is that we have data, public data up to here. And if you use the redshift space power spectrum from the BOSS DR12, the data release 12, and you constrain cosmological parameters, you will obtain competitive to Planck constraints on these cosmological parameters, not all cosmological parameters. For example, NS, the spectral index of the primordial power spectrum, the power spectrum coming from inflection, cannot be constrained very good because we don't have galaxies at such large scales. So both other parameters like omega m, h, the Hubble rate, are constrained as well as the Planck, as with Planck CMB the satellite. Okay, it is expected then that in this region, which is around the corner in 5 years, or 10 years, or 15 years, we will get better constraints coming from galaxy surveys than from CMB. Okay, one goal is to constrain cosmological parameters as the abundance of matter. The abundance of matter could be 0.301 or 0.302, and I don't care too much about this 0.01 difference. I will be more interested, and people in general is more interested to find new physics. And there are several indications that there are new physics. For example, the well-known H0 tension, and also the well-known sigma 8 tension. So the goal is not only to have better measurements of cosmological parameters, but search for new physics. For example, which is not a new physics, but we can measure the absolute scale of the mass of the neutrinos, and you can give it for granted. In the next 10 years, cosmology will measure the absolute scale of the mass of the neutrinos. But there are other questions as what is the nature of dark energy, or is gravity as GR is correct? We can also try to ask these questions. So the later test GR is the subject of and the motivation of this work. So, for example, here I am showing you the power spectrum, the redshift space power spectrum. I am showing only the monopole for two different models. One is GR, the one in blue, and the other is named F5. F5 is a kind of F of R theory. It is an F of R theory, but it is close to GR. The interesting thing about F5 is that F5 is allowed by CMB measurements, is at the edge of the allowed range, but it is still allowed by CMB measurements. And here are the differences. I am using some simulations because we don't have observations of F5, especially if you believe that the correct theory is GR, which is the most plausible scenario, but we want to find deviations, of course. So I am using the Bauger-Lees elephant simulations, which are the state-of-the-art of modified gravity simulations. And there is nothing special about F5 of F of R theories. This is a special case of the Hu-Sawicki theory, F of R. You can take it as a toy model, which is representative of F of R theories, or in general for modified gravity theories. But the advantage of using Hu-Sawicki model is that there are a lot of development about that specific theory, and there are also simulations about that specific theory. And the best simulations are in Hu-Sawicki and in NDGP. I will show you some results from NDGP in a moment. So the differences are actually small and overlap. The error bars of the simulations overlap. So what is the problem here? The theories are actually quite different. the problem is that modified gravity, I am talking about modified gravities that aims to explain the accelerated expansion of the universe. Well, this modified gravity invoke a screening mechanism that recovers GR in certain limits. These are, for example, small scales or high energy density, and by high I mean the densities we are in our solar system or even in our galaxy. For example, our halo has 2 or 3 orders of magnitude more density than the average density of the universe. Okay, so the standard statistics use it in cosmology as a power spectrum, as I showed you in the previous slide, give the same weight to all observed objects. Well, this is a little problematic because this is a snapshot of the cosmic wave in a simulation that is named the Quixote suite of simulations. And you can see the blue regions are regions that have almost no matter. These are the voids. And almost all the universe, well, or a large portion, a large share of the volume, of the total volume of the observed universe is given by voids. So what the power spectrum is doing is that it gives, given that it gives the same weight to all matter, you are actually probing the regions which are in red color, like the regions, and a little bit the filaments, and the voids are underrepresented. Underrepresented in the sense of the total volume. Okay, but that also implies that you are probing regions where there are too much matter. So you are probing regions which are screened. So for example, I am giving you here the basic picture of one screening mechanism, which is the more known, perhaps. And by the way, it is the screening mechanism that FOFR uses. So you have a scalar field that mediates a field force. However, its effective potential, the whole potential, is composed of two pieces. One is the potential in vacuum, and the other one is the potential when your particle test, your test particles are in an environmental densities. It turns out that the mass associated with this potential is quite large when you have high energy densities in the environment. This means that that the range of the field forces are very small. Indeed, they are smaller than a micrometer, so they are actually screened for all the current test of deviations of Newtonian gravity. Okay, so this is the basic picture. So how can we do to exploit this mechanism in our favor to try to test gravity? So for example, this is the same plot. So I added the theoretical curve for F5, but with no screenings. I simply switch up the screenings. By the way, these solid lines are computed with perturbation theory, with the methods Jorge talked about in his talk. And this is the non-screened. The dashed line, the dashed curve, is the non-screened F5 model. So actually they are very different, and the differences are more easily seen, but of course by construction the power spectrum uses gives more weight to screen regions. But it is natural to ask whether we can do better. So, for example, what can we do if we start to probe inside voids? So voids are regions where there are less uh, less matter density than the average matter density of the universe. The average matter density of the universe is the one that gives you the Hubble flow. So there are regions that have less matter than the average. So I would like to construct statistics that prove that test this region. So this is not as easy as it seems at first place. There are a lot of systematics that one has to take into account. One has to define what is a void, a precise definition. Voids are not spheres, but they have complex structures, so and so on. So this is the paper of Martin White that started this area in modified gravity and in general in cosmology. So one constructs marker statistics to probe cosmological regions where screens are not efficient. So I want to basically prove voids. So I will construct a marked density field. So the idea is to take the overdensity field, which is defined in this way. This is the standard definition of the overdensity field in cosmology. Sorry. And define a mark function. It is a functional, actually, of delta, of the overdensity. And this is a special functional form, but it can take other functional forms. For example, an exponential, or things like that. But this is the one that has been studied in simulations. So if these two parameters are positive, this mark upweights low density regions. So instead of I define what is a void and all of that, I simply will take a look at regions that have low density regions, and I will upweight those regions. So what is delta R? This delta R, which appears here, is the overdensity field average over regions of size R. So it is the smooth density fluctuation. It is this expression which is widely used in cosmology for almost everything. You want to do perturbation theory, you want to do effective field theory, if you want to do biasing theory, you have to smooth density fields. But the difference here is that the R here is large. I want an arch sufficiently large that covers...
We are not hearing.
Sorry? I don't know.
I am hearing very well.
Sorry, somebody talk? Somebody have a question?
No.
Okay, I will continue. So, the difference there is that this R is of the size of about the size of the voids. And what we done at the end is to weight the density field, the original density field, by the mark function. So this is the mark function. I am divided by the average mark by convention, but this is not entirely necessary. So it is a 4-step process. One starts with the density field, which is a random density field. At each time space, it takes a value. And one smooths over large regions, and one obtains this smooth version of the density field. And one constructs the mark with this smooth density field and obtain this green curve And at the end, one waits with the original density field, with the mark, and one obtains this kind of curve. So the interesting thing is that regions which have high densities becomes underweighted, while regions which have low density becomes upweighted. And then we are doing what we want to do. We want to upweight regions of low densities. So screenings are not efficient in these regions. So for example, this is a snapshot of a paper of Lena Massara and collaborators, which in the top, which is the same cosmic wave I presented uh, 4 or 5 slides ago. One has this region, and this is the market density field. If you can notice that one is the negative of the other, where there is a void here. The mark density field is large. So I will make the same statistics, the same power spectrum, the same correlation function, but with this second snapshot. So now I go to the mark correlation function. This is a two-point correlation function, two-point configuration space correlation function of marked fields. Basically, we are going to do the same. So one have this like kind of estimator, which I will sum over all pairs I and j, given that the separation between both is a fixed distance. So this is a function of that distance. So, okay, this maybe be a little technical for observational purposes and simulation purposes, but for an analytical treatment, it is convenient to rewrite the above equation as in this form, where this 1 plus chi is the standard correlation function, and this new 1 plus w is the one thing that is named the weighted correlation function. And one construct this kind of correlations. So R is the difference, but we are assuming, as usual, a statistical homogeneity. So anisotropic, statistical homogeneity and isotropy. So R is just a scalar. Okay, sorry. I am noticing that I'm giving a little slow. So, for example, this is an example of what is a standard correlation function. This is in redshift space. So in redshift space, one takes the monopole, the quadrupole, and the hexadecapole, and higher even Legendre moments. And this is why they look, and this is how a mark correlation function looks. So the differences are larger in the mark correlation function case. So we want an analytical description to can compare this with theoretical templates against observations up to now to simulation only. So we have this double convolution. It is a 6-dimensional integral. So to those familiar with Lagrangian perturbation theory, can note that this one is related to the Seldovich approximation, to the correlation function Seldovich approximation. This is because this function C, these are the two matrices A and C, and they take this form, but they are only functions of little q, not of capital Q. So if I integrate these against 1, since this is a normalized Gaussian function, this gives me a 1. So this integral can be made immediately to give just 1, and one obtains the standard correlation function in the Seldovich approximation. Then it appears this I. This I is a function that has like 30 terms. It depends on what perturbative order you want to be. But it contains the one loop corrections, it contains the biasing scheme, and it contains the details of the mark correlation function. So I am not writing here. You can find the full expression of this I in this paper. And moreover, we don't solve this six-dimensional integral. It's very hard and very slowly. So we take approximative schemes to do it. All of them give very similar results. I will show you a plot. Other thing is the biasing. The bias is the fact that tracers, that are the things we measure, not the invisible dark matter. Tracer can be halos, galaxies, quasars, and so on, Lyman alpha forest, are biased objects of the underlying Coulomb field. So for me, it is different in modified gravity than in GR, because formation structure is more efficient in modified gravity than in GR due to this extra fifth force. And I am assuming that the fifth force is mediated by a scalar field, so it is attractive. So this implies that the system becomes relaxed more rapidly. And in turn, this implies a smaller bias in modified gravity than in GR. So, for example, this is the standard halo correlation function for different FOR theories. F6 is closer to GR, F5 is closer to GR, and the largest deviations of GR is F4 from these three modified gravity models. And each one has a lower bias than the next one. So I am using this for this range of halos. I am testing this with halos from the elephant simulations. And I am showing you the fact that the bias in GR are closer to one, in modified gravity are closer to one than in GR. So there is this problem that biasing is changing the form of the correlation function and all of the mark correlation function. And it turned out that these two effects are degenerated. So when matter, only matters, I take the cold dark matter, invisible cold dark matter, but visible in simulations, and compute the mark correlation function and obtain this. But I do the same for halos, and I see this inverted pattern. So this is one of the complications, and this is one of the things that will make difficult to compare with real data. Okay, so this inversion in the trends of the different theories. So other thing which is interesting is that if I am testing regions of low density or regions with low density, it is expected that this I have almost no time. I noticed that, Alfredo, thank you. It is expected that they are highly linear. And in fact, this is highly linear. And this is what I'm showing here. And I am here showing you some comparison of models. This is the model, the red one. Actually, all these models are proposed in this paper, but the one that this name, this work, is the one that we think is the best. And this is, we are comparing models to data. And yes, this is the one that works better, the one that is named. This work for different modified gravity models and GR. So this is the mark correlation function for halos, which actually, it is very promising that it works so fine. And there's also this thing of the Mach power spectrum, but I noticed that I have no time, but I will take 1 minute only. Okay, you can stop me if you want, but okay. The point is that if we can make 30 seconds, the same play, but with the Mach power spectrum, and yes, we can do it. And we have new parameters. We need to renormalize the theory because it is more complicated. But after you do all that mathematical games, you obtain a very nice comparison to, again, to simulations. Okay, so I stop here. So my conclusion is that this method will be taken seriously in the future, and up to now, it is giving promising results. So thank you very much. Alfredo, thank you.
Thank you. Thank you for your interesting talk. Did we have time for one question? There are no questions. Then we thank Alejandro Avilés for his talk. Okay, the next speaker is Joao Paulo Besa Brito, and he will talk about the scalar field in Schwarzschild de Sitter space-time, circular orbits, and synchrotron radiation. Please, Joao, your floor is yours.
Okay, thank you. And hello, everyone. I am a PhD student of the graduate program in physics at the Federal University of Pará, Brazil. And today I would like to share some information about geodesic synchrotron radiation. And this presentation was based on this work referenced here, and was made in collaboration with Rafael Pinto Bernay and Luis Carlos Bassalo Crispino. And well, this is the outline of the presentation. I will start with a brief introduction of the references and the history involved. And then I will revisit some features of the Schwarzschild de Sitter spacetimes, and that is our background here. And we will analyze circular geodesics that is necessary to the investigation. Well, we quantize the scalar field in the static patch of this space-time using canonical quantization prescription, and using interaction theory, we will calculate the emitted power by a scalar charge that moves along circular paths in the vicinity of the Schwarzschild de Sitter black hole. And for this, we will use numerical computations. And finally, some results and remarks. And well, the history begins with the reported evidence for gravitational wave by Joseph Weber, and a goal believed to be impossible at that time, during the 60s. And in this paper, from 1969, he concluded that his detectors were excited by gravitational radiation. And at this point, Weber became a very famous person, but we all know what happens later. Indeed, he did not observe the gravitational radiation. But it was interesting because many people tried to interpret his observational data, and interesting physics arose. For example, in this paper of Misne from 1972, he suggested that if the source was in the galactic center, and a reasonable explanation could be the emission of synchrotron gravitational modes by the galactic center. And in fact, it was a reasonable explanation, and it was inferred in this other paper here by Misne and others that the geodesic synchrotron gravitational radiation must exist, and inferred by an analysis of the scalar radiation setting. and where they considered a scalar charge moving along circular geodesics in the equatorial plane of a Schwarzschild black hole. But it was soon realized 1 month later that the spin of the field plays an important role. In fact, a crucial role, because in the case of the gravitational scenario, the lower multipolar modes have the major contributions, especially the quadrupolar one. And this was reported in this other paper, this other very famous paper by these prominent people, Mark Davis, Remo Ruffini, that together with Abdul Salam founded the Master-Grossman meetings in 1975. And the well-known Frank Zerilli and this other guy here, Jaime Tiomino, and that he was a prominent Brazilian physicist, a close friend of John Wheeler, and they worked together in the wiki theory interaction. And due to his contributions, Jaime Tiomino was nominated to the Nobel Prize of 1987. And well, he was born in 1920, and in the last year we celebrated his centenary here. And well, and even though Joseph Weber did not observe the gravitational radiation, these calculations that I mentioned here and have their own importance, because the radiation emitted by inspirali matter into black holes play an important role in high energy astrophysics. So, this kind of phenomena can be analyzed through a semi-classical approach that is using quantum field theory in curved space-time at tree level. And this starts with Crispino, Iguchi, and Matsas in 2000, when they considered the scalar radiation emitted by a scalar charge and scalar charge moving along circular geodesics in the equatorial plane of a Schwarzschild black hole. But it is more interesting because their formalism can be readily adapted to investigate other very interesting processes, such as the interaction of Hawking radiation with sources outside the black hole and so on. And well, since then, other very interesting papers have been published so far, analyzing this kind of phenomena, especially in the asymptotically flat spacetimes. And it could be interesting to seek what happens in spacetimes that are not asymptotically flat. Because in the late 90s was showed up experimental evidence that our cosmological neighborhood is undergoing accelerated expansion. And this was reported by Hayes et al. And Permut et al. In these two very famous papers. And this gives motivation to analyze physics in spacetimes that has in spacetime that has a positive cosmological constant. And a simple model that features this was obtained still in 1918 by Friedrich Kotler. And for the solutions that he obtained that have positive cosmological constant are now called Schwarzschild de Sitter spacetimes. So our goal in this work is to compute the emitted power, the scalar emitted power, by a scalar charge that are moving along circular geodesics in the vicinity of a Schwarzschild de Sitter black hole. And for this, we must calculate the one particle emission amplitude using interaction theory. Here in figure 10, we show a pictorial representation of this kind of phenomena, that is a small particle moving in circular orbits and emitting radiation in this embedded diagram of the Schwarzschild de Sitter space-time. Well, so the Schwarzschild de Sitter spacetime is a spherically symmetric vacuum solution of GR field equations, characterized by two parameters, that is the positive cosmological constant and a black hole mass. And the solution is given, the line element of the solution is given by 1, where the radial function is given by 2. And this space-time features two horizons, and the position of these two horizons can be achieved by the roots, by considering the roots of the radial function. And we recover the de Sitter space-time by putting m equals 0, where the horizon position goes to 0 and the cosmological and horizon goes to the de Sitter radius. And the Schwarzschild space-time can be recovered by putting lambda equals 0 when the event horizon position goes to 2m and the cosmological horizon goes to infinity. And here in figure 11 we plot the radial function of the solution. We see that for the Schwarzschild solution here, there is one root that represents the position of the event horizon. But when the cosmological constant is positive, we have two roots marking the position of the two horizons. And beyond the cosmological horizon, the space-time is dynamic as well as inside the event horizon. But between these two horizons, we have a static region that will be interesting to our case. And in this region, we have here the photosphere, the position of the photosphere that do not depend on the value of the cosmological constant, and a position Rmax that is the maximum where the maximum of the function f occur. Well, in order to have a black hole structure in this space-time, the value of the cosmological constant must be constrained in these two values here, between 0 and 1/9. In this extremum value here, the two horizons merge at the position of the photosphere. Well, the geodesics of this space-time can be derived using the Lagrangian 6. And due to the symmetry of the space-time, we have two Killing vectors at the equatorial plane. From this, we have two integrals of motions given by 7 and 8. In the Schwarzschild space-time, these two quantities are called the specific energy and specific angular momentum of the geodesics. And putting this into the Lagrangian, we obtain the ordinary differential equation that governs the geodesic, the motion of the particles. And here, epsilon is 0 for null geodesics and -1 to time-like geodesics. Well, the circular geodesics is obtained by the vanishment of the r dot and r double dot. And we obtain these two conservative quantities here along the circular orbits. And due to the fact that these quantities are real ones, the existence region for the circular orbits are another one that is limited by the photosphere and upper limit Rmax here, given in 12. Well, we can calculate the angular velocity of the time-like circular orbits given by 13, and where this angular velocity goes to 0 when capital R, the position of the orbit, goes to Rmax here, and goes to a maximum value when the position goes to the photosphere. We can analyze the stability of the circular orbits by computing the second derivative of the central potential, or by perturbing radially these orbits. In both cases, we obtain this in the equation here, and that is defined as this function capital F. And in order to better analyze the structure, the stability structure, we plot this capital F function here. And for the points of the surface that are above the hatched plane, that is, the hatched plane is defined when F is 0, and we have stable circular orbits in these regions. And for the Schwarzschild case, one can see that represents this face here. One can see that F is larger than 0 for R larger than 6m. But in the Schwarzschild de Sitter case, we have a inner stable circular orbit and an outer stable circular orbit. And for lambda larger than this value here, we have no stable circular orbits at all. Well, the scalar field dynamics in this background, it can be derived through this action 15. Varying this action, we obtain the Klein-Gordon equation given by 16, and a positive frequency solution to the Klein-Gordon equation associated to the time-like Killing vector, partial t here, is given by 17, and due to the symmetry of the space-time, we can separate the variables in this form here, and where this square root is just a normalized constant that will be useful later. And there are, in fact, two kinds of, two independent solutions in this case, that is the so-called in solutions that denoting mode spiraling coming from the past cosmological horizon, and the so-called up solutions denoting mode spiraling coming from the past event horizon. And well, the Klein-Gordon equation can be put in this form given by 18 here, where we have defined the effective potential given by 19. And due to this factor here, we see that the potential vanishes at both horizons. And when plot this potential here, one can see that the potential over here decreases as we increase the value of the cosmological constant. Well, we can further simplify the Klein-Gordon equation by considering the tortoise coordinate given by 20 here. The Klein-Gordon equation acquired this form given by 21. And due to the vanishment of the effective potential, we can obtain the analytic solutions in the region close to the horizons. These solutions is given in 22 and 23. For the in and up, so for the in and up modes, here capital A is just a overall normalization constant that we will obtain it later. We will obtain later, and the curly T and curly R are related to the transmission and reflection amplitudes. And by considering the Wronskian of these solutions, we obtain this flux conservation here, given by 24, that turned into be a probability conservation. And by considering the Klein-Gordon inner product here, and we auto-normalize the modes. Here in this inner product, capital sigma is a hypersurface, Cauchy is a Cauchy hypersurface, and one can show that this inner product is invariant under deformations of this hypersurface. And because of that, we can, for simplicity, choose the T constant hypersurface, and that have this unity vector or orthogonal, this orthogonal unity vector here. And so imposing the orthogonality relation for the modes U given by 26, we finally obtain the overall normalization constants for the modes given by 27. Well, following the canonical quantization prescription, we state the commutation relations for the annihilation creation operators given by 28 and 29. And we expand the field operator in terms of negative and positive frequencies, in which the coefficients of this expansion are the annihilation creation operators. And the vacuum state can be defined as in the usual way in a static space-time, that is the state destroyed by all annihilation operator here. And from the vacuum state, we can construct the one particle state by applying the creation operator in the vacuum state, as given in 32. Well, the source in the vicinity of the black hole is described by the normalized current given by 33, and here we consider it in the equatorial plane without laws of generality, because the space-time has spherical symmetry, and this is the full velocity of the source given by 34 here. And in the interaction theory, we add to the previous action and interaction term, given by this, that is a product of the current and the field operator here, given by 35. And using this interaction term, we constructed the scattering matrix or the X matrix operator. And with this S matrix operator at leading order, we can construct the one particle emission amplitude given by 36. And expanding this equation, we obtain the condition given by 37. That means that the frequency of the emitted quantum is proportional to the angular velocity of the source, and the proportionality constant is the azimuthal number. And okay, so the partial emitted power is given by the equation 38, and in which the capital T represents the whole range of coordinate time, and that turning to be proportional to the delta Dirac delta function. Sorry. And so explicitly, we obtain the equation 39 for the partial emitted power. And one can see that due to the presence of this term here, the power goes to 0 at the photosphere. And what we must calculate here is the capital Psi function, that is a solution of the radial differential equation. And in our case, we use numerical methods to do so. And furthermore, we can substitute the radial position of the orbit using this relation here and put the dependence in with an observable quantity, that is capital omega. Well, the total emitted power can be defined as in 40, and that is summing all contributions of the azimuthal and angular quantum numbers and the in and up solutions. Well, once we are dealing with numerical methods here, we have to truncate this sum in the LI index and at a maximum value. So in figure 14, we plot the total emitted power by the source, and for different choices of the truncation value, and for lambda equals 150 to -1, and one can see that the total power starts from 0 when the position of the object is at Rmax, and then reaches a maximum close to the photosphere, and decreases to 0 at the photosphere that is represented here by this vertical gray line. And we also see that for the orbits far away from the black holes, higher multipolar modes do not contribute for the emitted power, but this behavior changes when we approach the photon orbit, in which higher multipolar modes becomes relevant, and in this region the source are emitting synchrotron modes. And this still remains when we increase the values of the cosmological constant. For example, for this, for lambda equals 15 to -1. And in fact, this behavior still remains for all allowable values of the cosmological constant. So the source always emits synchrotron modes, at least near the photosphere. And it is interesting to see separately the contributions for the in and up solutions. But before that, I would like to mention that more than 95% of the emitted power comes from the modes L equal M, and at least near the photosphere. And to see that, we define this capital theta function here, that is the power with the contributions just to the L equal M mode over the power considering all contributions of the azimuthal number. And one can see that this ratio goes to 1 near the photosphere of the black hole. And because that, in the next results, we consider just the L equal M contributions. Well, and here in figure 17, we have contributions for the up modes, left in modes, and right. And when compare these for different choice of L equal M, obviously, and lambda equal 150 to -1. And when we compare these results with the Schwarzschild case, we see that there is almost that is very similar. But when we look closer, we see that there is an enhancement in lower multipolar modes. And when we increase more the value of the cosmological constant, we see that this effect becomes more evident. In this case, for lambda equal 50 to -1, for example, the peak of the power have almost the same height here. And this still occurs for the up solutions here when increasing more the value of the cosmological constant. And well, in spite of this enhancement of the lower multipolar modes, we still have emission of synchrotron modes near the photosphere and for our allowable values of the cosmological constant. Well, here are some final remarks. We numerically calculated the partial and total scalar emitted power emitted by a source in the vicinity of a Schwarzschild de Sitter black hole using a semi-classical approach. And we showed that the total emitted power strongly depends on the value of the cosmological constant. In particular, there is this enhancement of the lower multipolar sector. And this turned to be the opposite that occurs in the anti-de Sitter spacetimes, as was reported by Cardoso in 2002 here, in which he obtained that higher multipolar modes are enhanced and when we increase the absolute value of the cosmological constant. So as further works, we can analyze fields that have non-zero spins, like the electromagnetic and gravitational and radiations, and we can analyze it too in more generic spacetime as de Sitter spacetime. So here some references and my acknowledgements. Thank you for your attention.
Thank you very much, Joao, for your interesting talk. We have time for some questions. Please raise the hand. Okay, if there are no questions, we thank Joao once again.
Thank you.
Okay, the last speaker is Elias Castellanos Alcántara, and he will talk about dark matter as a condensated phase of generic bosons. Please, Elias, the floor is yours.
Thank you, Alfredo. Let me share my screen. Can you see it?
Yes.
Okay, let me start. Hey, thank you to the organizers, Alfredo, Carlos, for giving me the opportunity to talk to you some results that I am working for the last 2 years, right? So, as you say, the title of the talk is Dark Matter as Condensed Phase of Generic Bosons. So this is a toy model that I will show you, which is in which we insert, let's say, in some curved space-times, some scalar cloud, in order to compare or interpret this situation as dark matter, right? So we will assume, or I will assume from the very beginning, that the system is in some kind of Bose-Einstein condensate, right? So if we compare with the with some with some observations, so we obtained that in order to fit with some rotation curves of some galaxies, we need to supermassive black holes, right? In very, very, very small mass for the boson particle, right? And also, we obtained from this analysis that the interaction between particles inside the condensate or inside of this scalar cloud are very, very small. And let's say the system behaves like some kind of a ideal condensate, right? So in order to analyze these rotation curves, we will use the Thomas Fermi approximation, right? Which is commonly used in the usual BECS in laboratory. And as a pivot model, we compare with the Navarro-Ferrand-White, right? And then we can conclude that this model fit more or less good the observations. So this is the contents of the talk. I will start with some kind of introduction about BECS and the relation of scalar fields and BECS. And then the main point, or the core of the talk is the interpret these Klein-Gordos fields as a BECS in this curve background, specifically in a Schwarzschild de Sitter space-time, and then compare the other results with the observations. In this case, with rotations curves in galaxies, right? And then some conclusions in perspective. From the very beginning, what is Bose-Einstein condensate? Bose-Einstein condensate is a quantum phase transition, right? That appears at some critical point for bosons, in which when you decrease the temperature, now the quantum effects become relevant. At this point, all the particles that form in the condensate of the system goes to the ground state. Almost all the particles. If we can, we are able to get the zero temperature, and then we can obtain a pure condensate, but it's not possible because some laws of thermodynamics. So then, in this way, this transition is a new state of matter, right? And there are bosons in these systems. What is the relation between scalar fields and BECS, which is very, very complicated, right? Because this is still an open field to study, right? So, but these scalar fields appears in many theories of gravitational theories, right? Also, in a large number of hypotheses, in these higher dimensional unified theories, dilaton in string theory, inflatons or dark matter in cosmology. So the important thing is that this line of research was, I mean, is more, let's say, a study with the Higgs boson was detected, which is in fact an scalar, no? So, for instance, in cosmology, we have this kind of scalar fields that the people say, or the people call inflaton, dilaton, quintessence, phantom, Galileon, etc., etc., etc. So, these kind of things, or led us to think that there's a fundamental relation between particle physics, cosmology, and condensate matter. So we have, like right here, a lot of references about this topic, right? But what is the good thing? I mean, the new thing in this kind of scalar field models, right? In principle, we can associate a boson with this field, and then if the particle is a boson, they not fulfill the Pauli's exclusion principle. So under certain circumstances, we can put all these particles in the same quantum energy level, right? This is an open question also. What are the conditions in which this kind of scalar fields can form this kind of BECS? or what is the nature of the transition or the phase transition in this kind of system. This is an open question, even in a flat space-time, right? So the main thing here is that we can associate a boson, and then under certain circumstances, we can put all the bosons together in the same quantum level, or try to make a phase transition. And then what is important for this? Okay, let's say that the Klein-Gordon fields can be interpreted or viewed as a relativistic Bex or not. More than that, there is a lot of works that suggest that this kind of Klein-Gordon fields can form this kind of phase transition of this Bose-Einstein condensate, right? However, as I was telling you before, this topic is not fully understood, even in flat space-time. Okay, so even more, these scalar fields of generic bosons that I call can be viewed as a serious candidate to describe dark matter. So, and then we have this trichotomy, right? If the scalar fields are Bex, and dark matter can be viewed as a scalar field, dark matter can be viewed as a Beck. And the answer, of course, is I don't know. But fortunately or unfortunately, we don't know what is dark matter, right? And then it's plausible to study the composition of this dark matter in the universe as composed by some kind of generic bosons in the form of Bose-Einstein condensate. So this is the main idea in this talk, and then let me explain, let's say, in some specific cases, right? And so for this goal, there are these 4 papers that are published already. So I will want to talk about this a little bit, right? And then we have never forget that this is an approximation, because I will use the Thomas Fermi approximation, and the equation of motion of the corresponding system is the Gross-Pitayevsky, some kind of Gross-Pitayevsky-like equation. So let me in this kind of things. So let me consider this spherical, symmetric, and static background, in which the metric is this one. Now we have here the metric function, right? And as usual, this is the angular part. Of course, we have the Einstein equations, in which we have included the cosmological constant, let's say. And let me insert in this curved space time a scalar field with this kind of potential, right? In which this is the mass parameter of the scalar field, and this lambda in here is the coupling constant. Now we can interpret this coupling constant as some kind of how the particles inside the system interact. Okay, as you know, this is the Klein-Gordon equation for this kind of systems, right? So let me use this ansatz, let's say. Okay, if we insert this ansatz in the Klein-Gordon equation, and with this kind of with the help of these coordinates, the star coordinates, okay, we can obtain this this equation, which is some kind of nonlinear Schrodinger equation, right? But this equation is precisely the the Gross-Pitayevsky equation, right? We can see here that we can obtain this effective potential, which depends, of course, of the metric functions and the mass parameter of the scalar field and some derivatives of the metric function, right? Also, we have here this is the density, and this as you remember, this lambda is the self-interaction term. So we can see that if we introduce these ansatz and these coordinates, we can modulate interaction within the system, right? They are, of course, modulated by the metric function. So this is the corresponding equation of associated with the system, and this is some kind of Rospitayevsky-like equation. So in principle, this is very hard to solve, right? Because it's a nonlinear equation, and then you have inside the metric and so on. But if we let's say use some formalism behind Bose-Einstein condensation, is quite easy to obtain some information as a first approximation. So let me go to the Schwarzschild de Sitter space-time. So as it was mentioned before, the last talk, this is the metric function in this case. So let me construct these dimensionless quantities, and then I can rewrite the metric function in this form. And the effective potential now is given by, in a dimensionless form, of course, is given by this equation. Okay, this is I will interpret this as some kind of trapping potential that can contain some quasi-states of the scalar distribution around this black hole. So let me show you here different values for this is the potential, the effective potential, or the trapping potential, right? And then if we set the mass parameter of the mass of the scalar field equal to 0, we don't have regions in which we can confine the system, right? Also, we have here some critical mass in which there are no regions to confine the scalar field around this black hole, right? And also, because we have a cosmological constant, then we have a cosmological horizon, which is not dependent of the values of the parameters involved, okay? So we're interested here in this, for example, in this region in which we can contain or trap the scalar configuration of the scalar cloud of the Beck or dark matter in this case, right? Okay, let me apply then, in order to obtain a solution for the system, the so-called Thomas Fermi approximation, in which we are able, if we assume that the potential energy and the interaction energy are bigger than the kinetic energy, we are able to, in principle, and within the order of approximation, we are able to obtain solutions which are formally solutions to the system viewed as a Beck, right? So in this case, this complicated equation of motion, which the Rospitayevsky equation, can be written in a very let's say very easy form, right? In which we are able to obtain solutions for the density. And then in the Thomas Fermi approximation, we are able to obtain solutions for the density of the system, right? And which are valid in this for these conditions, right? This is this omega is the frequency. It's a real frequency of the field, of the scalar field, or of the Beck, right? And this is the effective potential, and you can see here also that the interactions are modulated by the metric function, right? Okay, so also in dimensionless form, we can write the density, okay? And after all these very straightforward calculations, we are able to obtain, for example, the density in function of the parameters involved. With this condition, we are able to obtain the size of the cloud within the approximations, I mean, in which the Thomas Fermi approximation is valid. And also we can obtain, for example, the number of particles in the cloud or in the Beck. in this case. So let me show you here also for some values of the parameters involved. This is the trapping potential, right? This part is not physical. So this is the density of the scalar cloud. So you can see, and also can be proved that the maximum of the density is situated in the minimum of the potential. So there are regions in which we can obtain these stable configurations, right? And we can interpret this as a dark matter in principle. So let me go further and let me compare this model with this galaxy rotation curves, right? And this is published in this paper in here, if you are interested. So I will take the as a pivot model. This is the well-known Navarro-Ferdinand White, right? This is the so-called isothermal, sorry. And this is the density for our model for the in the Thomas Fermi approximation for the back. So you can see here the profiles of the densities associated with each model, right? So we can hear the Navarro-Ferdinand White. No, we have these problems of divergences in the center and so on. We have here the isothermal, and this is the black one is the density corresponding to the Bose-Einstein condensate model in the Thomas Fermi approximation. So the next step is compare with this Spark database. So, and we have here, for example, this is the Navarro-Ferdinand White for different galaxies, right? This is the Beck model. We can hear the different colors represents, for example, the stars, the gas, the bulb, right? In the black one, here is the model of the Beck. And the total contribution of all these things is this line, right? And you can see this is the observed data. And this is the Navarro-Ferdinand White with the same characteristics, right? And then we can see that our model is more or less good in this approximation, right? According to our results, apparently the Thomas Fermi approximation is useful up to a few kiloparsecs, right? Because it's, as you remember, this is only an approximation. It's valid in a certain region, right? But give us some insights, very, very interesting, related to the nature of this scalar cloud or Beck or dark matter that we interpreted in this work. The good things of this is that we have just one galactic parameter, no, only the mass of the black hole, right? And then we are thinking if we have to extend this study to dwarf galaxies or spiral galaxies and study this supermassive black holes in the center of the galaxies. But it's not, I mean, there is no new that there are observed a couple of supermassive black holes of this order of magnitude that I will show you. So this is a lot of galaxies in this Spark database base, and then this is the Navarro-Ferdinand White. Again, this is the Beck. This is the Navarro-Ferdinand White. This is the Beck model. So we can see that the model is fit quite well the observations. But what are the parameters that fits this rotation curves? The mass of the black hole is of order of 10 to the 19 to the 11 solar masses. Very supermassive black holes, right? Maybe we have to extend the validity of the Thomas Fermi approximation, right? But this kind of black holes, they were observed in these two papers, so there's not so, let's say, bad to obtain this kind of fits for the parameters in the model, right? And then we obtain also the mass of the particle of the boson order 10 to minus 23, 10 to minus 21, and the interaction parameter is of order, as you remember, that I say in the abstract, almost 0. I mean, the system behaves almost as an ideal Bose-Einstein condensate. This is interesting because we can this kind of studies lead to understand the nature of the dark matter for first principles, right? And then work to do this. I'm working on this already. An application to boson stars in this model. I mean, boson stars as a BEX, and extend this kind of model to black hole super rotations, analyze the vorticity, the accretion, rotation curves, lensing, etc. So I think that's all. Thank you very much.
Okay, thank you very much for your talk, Elias. We have time for some questions. Okay, if there is no...
I have a question. Well, a remark or question, I don't know. I think is analyzing the properties of lensing could be very interesting because, I don't know, there are many works in which one compute the rotation curves of galaxies, of stars in galaxies, and they are able to, I mean, to fit almost every model because you have free parameters there, and at the end you will end with some kind of fit for rotational curves. But when you consider these parameters fixed and go and make the lensing properties of compact objects in general, or black holes or whatever, but due to these scalar fields, the lensing properties will be very different than standard matter. So I would encourage to study lensing there and see what the differences could be to discriminate among models there.
Yeah, you're right. I mean, the model that I present was it's an approximation, right?
Yep.
We use the simple manner to solve the system, which is analytical. So we can obtain the density analytically. So this solution, of course, contains these limits of validity within the system. No? Then if I want to study lensing and accretion and all these things, I have to solve completely the equation of motion, right? And then obtain, let's say, some criteria to discriminate between different models. No? But this is a step in which I am working. So it's interesting because in a simple form, you can obtain a lot of properties of the scalar of the cloud around a black hole. I don't know if it is dark matter or not, right? But it seems to be like there are some way in which we can explore all these kind of properties, no? And for me, it's quite interesting because you're, let's say, mixing several branches of physics in a problem, right? Which is quite interesting, I think.
Yeah. Yeah. Thanks.
No, thank you.
Any other question, comments, or remarks? Then, if don't, We thank Elias once again.
Thank you, Alfredo. Thank you, Carlos.
Okay, that's all for this session. Be aware that the instructions for the proceedings will come soon. And thank you very much to all the participants. I don't know, Carlos, if you have something to say.
Well, just to thank all the participants, in particular the speakers, for the interesting talks, and hope to see you soon, face to face.
Yes. Okay.
Yes, indeed. Bye-bye. Nice
Thank
to
you
see you
very
guys.
much.
Thank you very much, guys.
Bye-bye, everyone.
Thank you, organizers, Alfredo, Carlos. Thank you very much.
Bye. And thank you.
See you.
Bye.
Bye.